Hi, this is a video that takes you through a GCSE demand type question on figuring out what to do with apparatus to find empirical formula. So the objective for this is to be able to come up with an experimental method to calculate the empirical formula for an experiment that perhaps you may not have been able to see in the laboratory of your school, because this is actually working with chlorine gas, and chlorine gas is a pretty nasty gas, I must say, to be able to deal with. And this experiment here in this diagram is a very simplified version of the actual apparatus that you have to set up. And there are very few resources that I actually found on the internet to tell you in great detail as to what to do, and very little to find out to use the apparatus to find out the empirical formula. So I just thought I'd come up with a video to take you through this. And hopefully you'll be able to use this when you are revising for your GCSE chemistry, and that will be useful. If it's really useful, leave a comment in the comment section below, and like the video, and of course, to keep up with everything, subscribe to the channel. It's most appreciated. So, finding the empirical formula. I need to be able to assume that you understand what empirical formula is. The empirical formula shows the simplest ratio in which atoms combine. From any regular formula that we actually have in chemistry, I'm sure you've been able to see formulas such as CH4 for methane, C6H12O6 for glucose. Those actually are able to tell us what masses of the elements combine. But what we can also do as chemists is we can turn things the other way around. If we actually know what masses combine, we can work out the formula using the concept of moles. So let's have a look at this question. This is aluminium burning in a stream of chlorine to form aluminium chloride. So you've got this very simplified picture of the apparatus. You've got chlorine coming in on the left-hand side. You've got aluminium powder. Any source of aluminium will work in reality. You can actually use aluminium foil, which you would find at your local supermarket. You need to start off the reaction with a little bit of heat from a Bunsen burner, and it's all contained in a glass tube. The chlorine and ideally very few of the actual products that are made will then pass through on the right hand side. So the question says, suggest how you'd use this apparatus to find the empirical formula of aluminium chloride. So I've left a little flowchart at the bottom, and this is essentially what you have to do. But what you also have to do is you have to propose what the masses are that you have to measure, and how to get the masses for your calculation. So the first thing that you'll have to do when you are working things out is you'll have to find the masses that combine in grams by experiment, and that's what this is all about. You don't have to change the number of grams in each of the masses of the elements to moles of the atoms. This is all because the mass of an aluminium atom, for example, is very different to the mass of a chlorine atom. The mass of an aluminium atom, in terms of its relative atomic mass, we can assume to have 27 units, and the chlorine atom, has a relative atomic mass of 35.5. So the chlorine atom has more mass in it. It would actually weigh heavier. So we can't just rely on grams in order to work out the ratio of the atoms in our compound. What we'll have to do is we'll have to change the grams to moles of atoms. And if you wanted to work these things out, you'd have to be able to use the formula number of moles equals the mass of the sample, or in this situation, the mass of your element divided by the relative atomic mass of the actual element, and we'll generalize that as molar mass. So number of moles equals mass over molar mass. That's how I'll be referring to that relationship from this point onwards. So once you have changed your grams to moles of atoms, you can then figure out what the ratio in which the atoms combine. There's a very easy, simple trick that you can do. You can divide your number of moles by whichever figure you have which is the smallest number of moles. And then what you have is you have you get given a couple of numbers. The smallest number will be 1. If you have any non-integer numbers, non-whole numbers, you'll have to just do a quick sneaky multiplication to get rid of these fractions, and you can just multiply everything. So if you see something like 1 to 1.5, if you multiply both by 2, you'll get 2 to 3. So you can then utilize that in a proposed formula for your empirical formula. It's very, very important for me to emphasize that. This will allow you to get the simplest whole number, simplest ratio in which atoms combine as whole numbers. Okay, it's very important that we don't confuse that with your molecular formula. You'll need some more data, some more details, primarily your molecular mass, in order to figure out what your final formula is. But it should your elements, your atoms in your the atoms of the elements in your molecular formula should be the same ratio as your empirical formula. So let's come back to this question now. Aluminium burns in a stream of chlorine to form aluminium chloride. Suggest how you'd use this apparatus to find the empirical formula of aluminium chloride. It's very, very clear that we need to work out what the masses are of our starting elements. So aluminium powder, very, very easy for us to calculate, or whatever source you have of aluminium. I'm going to show you a video, some video excerpts of this experiment that I've located, thanks to Cardiff University for the work that they've done in filming that, and that was supported by SEP and RSC. So I will be showing you some of those to make sense of this experiment. But in those videos, you actually use a roll of aluminium foil. It's actually convenient. So you can weigh your aluminium foil, figure out what its mass is in grams. You can then work out from that your starting number of moles of aluminium. Now, what you could do, and a smarter way of doing this, would be to actually make sure that you are measuring exactly the right mass of aluminium that you're starting off with. So in order to do that, you'd get a clean, dry glass tube. You would measure the mass of that. So you would weigh that glass tube, make sure that it's empty, make sure it's dry, particularly for this experiment as well. Then what you would do is you would add your roll of aluminium or your scoop of aluminium powder. You would weigh it again to find the mass of your aluminium. And then what you could do is you could then connect up the apparatus. You could connect up the chlorine to the glass tube. You would run your experiment, you would heat it, you would allow the chlorine to pass through. You would obviously have to assume at this stage that the aluminium chloride that forms as a result of the combination between aluminium chloride stays within the glass tube. More on that a little bit later. And then you'd allow it to cool down. You would ensure that the experiment is complete. You could even repeat this experiment once you weigh it again, and you could repeat it, plus more chlorine. If the mass does not change, then that means that no more aluminium will actually be reacting with the chlorine. So once you've let it cool down, weigh it a final time, and that increase in mass is then down to the chlorine joining on to the aluminium. So you've got your final mass, which is going to be the aluminium combined with the chlorine for aluminium chloride, and that will also be added to the mass of the glass tube. So if you take away your second reading, if you take away the mass of the aluminium and the glass tube from the final mass, which contains the aluminium, the chlorine, and the glass tube, you will then work out what the mass of the chlorine is that has joined on to the aluminium. And that's really, really important, because from the mass of the chlorine, you can then work out what the number of moles of chlorine are that have joined onto the aluminium, because you divide that mass by 35.5, and that will give you the number of moles. So once you've worked out the number of moles of chlorine that have joined, once you've worked out the number of moles of aluminium that have joined, then what you would then need to do is you would divide both by the smallest number, whichever one is smaller. If it's aluminium, then divided by aluminium. If it's chlorine, then divide it by the number of moles of chlorine. You should actually work out, if everything is done correctly, that you'll probably get a 1-to-3 ratio in this particular case. Now, I'm going to make it a little bit more interesting and show you what the experiment actually looks like. So, as I said, great thanks to massive thanks to Cardiff University for having this. I'm going to have a link to their video so you can actually see everything all the way through. But be warned, if you are a GCSE student, I would suggest that maybe the commentary is slightly higher level than GCSE would expect. So what they do is they actually put the aluminium into the glass tube. So there's your glass tube. They've actually made sure that everything is dry, and the reason why is because your aluminium chloride that you form is it will actually react with water in contact with water. So you actually do want to have fully dry apparatus. So what they've done is they've had this apparatus. They've drawn they've drawn air. Well, before they actually add the chlorine, they've drawn air through, and they've used anhydrous calcium chloride to dry that air. So you can imagine that air is coming through here before the experiment is actually conducted. You've set up your apparatus. Air is being drawn through from right to left because you've got some sort of suction pump that is drawing it through. And now this person is actually ready to start the experiment. So there you go. There's the aluminium that goes in there. Okay, they're just temporarily replacing it with that, and now this is now going to be connected to the chlorine source. So your chlorine is going to be coming through, and this is another reason, another emphasis as to why it is. You probably haven't seen it in school because this kind of setup is particularly risky, particularly dangerous as well, especially due to the risk of the chlorine. So let's just play the video and see what's going on. So you've got the aluminium foil there. Now what's going to happen is, and the video jumps forward, you've now got chlorine going through. So there's a before, okay, and there's an after. You can recognize that chlorine as that kind of like green, pale green color. And now what they are doing is they are now heating it. So just quick, gentle burst from a Bunsen flame. You'll actually see that it is an extremely exothermic reaction. I'll just pause it over there and just bring it all the way through. So you can actually now start to see that the aluminium is reacting. And there we go. Okay, so you now are forming this aluminium chloride over here. Now, what you would have to do is once the reaction is finished, this is what you will have to then allow to cool down and allow to cool down so that you could reweigh it. Okay, so I have to assume that everything is done. All of the weighing is done. I think this experiment was just filmed just to demonstrate what was going on. Now. What you can see illustrated at the top, you wouldn't necessarily know if you were doing the question like this. Okay, so the best thing to do really would be to make sure that you work through questions like this, and if they give you data, that you work through it yourself. Now, I want to talk about the second part of this question as well. I want to complete the question and talk about what safety precautions are needed when carrying out this experiment. So I've already intimated that chlorine is very toxic, so you'll need to make sure that you conduct this in a fume cupboard. This is a fume cupboard, so it's basically a chamber that air is drawn through. You'll also need to have that chlorine when it's escaping out of the apparatus. You'll need it to be absorbed by something suitable. And modern day fume cupboards will actually have a bank of carbon which absorbs chlorine in. Carbon was actually used in World War II in gas masks. So actually, the carbon was placed in there because chlorine was actually used as a weapon in that war. So a nice little link to history there. And let's just see what happens. Now, the reason why I said that this was a little more complicated than your question suggests is because your aluminium chloride is actually very, very volatile. So if I just forward through, in the cooler part of the experiment, you'll actually form your solid aluminium chloride. The video, I will link the video to within the comment section, but the video also talks about an interesting property of aluminium chloride and how it actually dimerizes. So two AlCl3 molecules will actually combine to form AlCl6, Al2Cl6 rather, and I will encourage you to learn more about that if you are interested by taking out A-level chemistry. So this volatile substance, you can actually see that this is like after that glass tube, and what they have actually done is they've used soda lime to keep everything completely dry so that the aluminium chloride does not react at all. So this would be the outlet for the chlorine. No water is going to be coming in through there. No water can come in from the start on the left hand side, and where you see this ice is actually cooling down the outside of where this aluminium chloride is passing through and into a test tube. So this ice and any water that may form is not in direct contact with the solid aluminium chloride. You can actually see that aluminium chloride has been cooled down there. So it's a beautiful yellow color. Now, if you were to do this experiment using realistic levels of apparatus, you would also need to weigh the test tubes, all of the bits of apparatus that's connected to the glass tube, because as you realize, the aluminium chloride is escaping from the glass tube in order to make sure that our calculations are accurate and closer to the real true value of the empirical formula of aluminium chloride. You'd actually have to weigh and then take into account any differences, because the differences in the rest of the apparatus, any gains in mass, is due to the aluminium chloride. So this little trap, this little ice trap, hopefully contains as much of the aluminium chloride as possible. So I would suggest that maybe the glass tube on the inside, delivering it into the into the test tube, would be weighed, and any difference would be added, and also the increase in mass of this glass tube as well. It's an interesting diagram to show how chlorine and aluminium are combined together. This is well beyond GCSE. It's really, really interesting though. You can actually see that the chlorines form these lattices, these beds, these layers, and the aluminium just sits on the inside where the little tiny pockets are, where the little tiny gaps are. But it's not even, so you don't actually have aluminium over here, for example. It's just like a kind of like a zigzag over here, and then a continuation of a zigzag, like an opposite zigzag here, and that would happen on this side as well. So it's really, really interesting, definitely as a chemist. So like I say, I just want to give a big thank you to Cardiff University for posting this video. I've got the credits over there, so Peter Hollenby and Peter Edwards, thank you very much. You can see that the RSC, the Royal Society of Chemistry, have promoted this video and supported this video. So I'm just going to come out from there. So just to summarize, if I may, these are the different stages, these are the different steps. So what you would do is you would weigh the glass tube, weigh the glass apparatus, put the aluminium in, reweigh it to get your mass of aluminium. That gives you your moles of aluminium right at the very beginning. You would then have your chlorine. You would assume that all of the aluminium reacts as well. That's a very, very important one, because if you've got some extra aluminium left over, that's going to be a problem. So because some of your aluminium would actually contribute towards the mass. So I'm just going to run this to completion. So that is the reason why you need excess chlorine. So you can actually see all of the aluminium really is reacting there. We'll just see that one. Let that pass all the way through. Okay, so you'd continually heat it. You continue to make that aluminium chloride to make sure you can see the little Bunsen right at the bottom is heating and making sure that the rest of that aluminium is reacting. So Any gain is purely down to chlorine and combining with the aluminium, and none of that mass is just raw aluminium remaining behind. Okay, so very quickly, do the reaction, measure the mass again because you've got aluminium chloride. Measure aluminium chloride. That's the only that counts for the gain in mass. You've got chlorine that has joined onto it. So you work out your mass at the end of your aluminium chloride. Take away the mass of the aluminium, so you've got the mass of the chlorine, and then divide both values, the mass of the aluminium and the mass of the chlorine, by each of their respective relative atomic masses. So you divide aluminium's mass by 27, divide chlorine's mass by 35.5. You've got your number of moles, and then divide both of those mole numbers by whichever figure of moles was the smallest. So you turn the smallest number into 1, and the biggest number should be 3 times that, if it is consistent with our knowledge of empirical formula of aluminium chloride, which is AlCl3. Thank you very much for watching. I know that was a long description of what to do, but I certainly hope that has helped you, and good luck with your exams and your revision. Take care. Bye.